Okay, so today we're going to look at some applications of equilibrium and how to solve for concentrations at equilibrium, okay, if given initial conditions. All right, and the way this is different, so say you had a normal chemical reaction that went to almost completion. Okay, say you had something like sodium plus chlorine goes to sodium chloride. And if this reaction goes all the way to completion, okay, what we know is, say we had 2 moles of this and 5 moles of this. Well, we know that sodium would be my limiting reagent, and that this 2 moles of this would what? Convert all the way over to 2 moles of this. And we know there's no reverse reaction going on. Okay, so since it goes to completion, we can just use stoichiometry and mole ratio and say, oh, hey, here's my limiting reagent, 2 moles of this. I know it's going to convert over to 2 moles of sodium chloride. The problem is, within an equilibrium system, say you had this system, the synthesis hydroidic acid. Let me just fix that real quick. That's what I wanted. Hydroidic acid. Okay, that goes to HI. And you had 2 moles of this and 1 mole of this. Well, not all 1 mole of this is going to do what? Not all of it's going to go over here. Because at the same time, some of this, because some of this H2 or HI is also going to react back and go back to I2. Okay, so that's the problem with equilibrium. You can't just say, hey, all this is going to go over there, because some of this is going to go back. So if only we knew the ratio of products over reactants at equilibrium, or what ratio is it going to go to, well, then we could solve for the concentrations at everything at equilibrium. Well, luckily, we do know this. Okay, and that's exactly what our K, or equilibrium constants, tell us. So let's take a look. Let's solve one. Stick with that equation. Say we have H2 plus I2 going to 2 moles of HI. And the Kc for this reaction is equal to 51, and this is at 448 degrees Celsius. Okay, now the temperature, we don't have to do anything with the temperature, but remember, temperature is the one thing that's going to change my K values. Okay, when we think of that, it's going to change the thermodynamic favorability of the forward or reverse reaction, right? Because if we go back and think delta G is equal to delta H minus T delta S, so my temperature can change my delta G. And if my delta G is changing, well, that's going to change which reaction is favored. Okay, so we don't have to worry about it with K's. Just know that, remember that K constants or equilibrium constants are constant at a set temperature, because delta G is constant at that temperature as well. Okay, so there's my reaction. Let's go back and look at this. Let's say solve. I set this up wrong. I'll probably have to redraw that reaction, but we'll just go. Okay. Solve for the equilibrium concentrations if the reaction started with 1 molar, because we want concentrations, 1 molar H2 and 1 molar I2. Okay, so again, like we've been talking about, unlike stoichiometry, well, if it's just a 1 to 2 ratio, oh, there's 2 moles of this produced. Nope, because some of this is going to go back to the other way. All right, so what we're going to set up, if you remember from last year, is we're going to set up some ice charts. Okay, and just so remember what our ICE charts stand for, the I is initial, the C is change, and the E is equilibrium. All right, so let's fill in what we know and see what we can solve for. Oh, and one other thing that's always really useful to do is also write our K expression. So in this case, the Kc is equal to products over reactants. So it's going to be the concentration of HI raised to the second power, because that's my coefficient, divided by the concentration of H2 times concentration of I2. Okay, so that's what my Kc value or ratio is going to be. Okay, let's keep going here with this. So, initial. Well, I know I have 1 molar of this. I know I have 1 molar of this. And since the problem doesn't say anything, right before the reaction starts, I have 0 molar of this, right? I have no products before the reaction begins unless otherwise stated. So now, we know that something is going to happen to produce some HI. So we know that concentration of this is going to decrease, minus, and we don't know what's going to decrease by, so I'm just going to put an X, put a variable there. We know this concentration is going to decrease, so we have a minus. We don't know what it's going to decrease by, but I know the mole ratio. I know for every one of these, I have to use what? One of these. So my change is going to be the same. My change for HI is going to be a plus, because I can't decrease the concentration from 0, and also it's a product, so I'm going to be making it. I don't know what how much I'm going to make, but I know the ratio. I know for every one of these, I will get what? 2 of these when the reaction happens. So if my change is minus X here, my change here is going to be plus 2X. So then, I know the initial concentration. I know the change in concentration to reach equilibrium, so I know what the equilibrium concentration is, or I know an expression for it. It is 1 minus X. This one's going to be 1 minus X. This is 0 plus 2X. Or we're just going to say 2X. Okay, so now I have my concentrations, or again, expressions for my concentrations at equilibrium. And since I have concentrations at equilibrium, I can plug those back in to my Kc. So let's go ahead and do that and solve. So that's what we got here. We know the equilibrium constant was 51, okay, and that was given, okay, is equal to 2x quantity squared, sorry, my bubbles, 2x quantity squared, divided by 1 minus x times 1 minus x. All right, so, and now it just becomes an algebra problem, so let's go ahead and solve. I'll move this over here. So say 51 equals. Now I'm going to simplify something here. You could FOIL this and get a quadratic, or I'm going to actually simplify it to 1 minus x squared, because now I have a squared term over a squared term, so I can square root this side. I can also square root that side. You could FOIL and you get the same thing, but see how this simplifies it? Okay, so now we've got the square root of 51, which is 7.14, is equal to 2x over 1 minus x. So now I'm going to solve for x. So I'm going to get x out of the denominator, so 1 minus x, I'm going to multiply both sides by that. Distribute in. 7.14 minus 7.14x is equal to 2x. I'm going to add this term over to the other side. I'm going to come up with 7.14 is equal to 9.1. It's a 9. It looks a lot like a 2. It's actually a 9. 9.14x. Divide by 9.14. And x is equal to x is equal to 0.78. Right. So now we have my change. So what can I do with this? I can go back and I can put these into these expressions here. Okay, because I know what my change is. So I can then go ahead and solve out the rest of it. So we have x was equal to 0.78 So I have 1 minus 0.78, and I get 0.22, 0.22, and I have 0.78 times 2, and that gets me to 1.56. So here are my final answers for my concentrations. So remember, when we're solving these ice charts, well, why do we even have to set up an ice chart? Again, it's because systems at equilibrium go to a set ratio. Okay? So just because I start with 1 molar of this doesn't mean I'll get 2 moles of this. Right? It's going to go, in this case, it's going to go to this ratio of 51. Now, a good thing to do is always check, does my K rate constant match up with what my equilibrium concentrations are? So this is 51, so in this case, K is greater than 1, right? So this should be a product favored reaction. Well, it is, because I end with 1.56 molar of this, where my other two are less, so it is product favored. So again, with this also tells me that delta G is going to be less than 0, or that forward reaction is going to be favored for this. All right? So there's a quick intro or a review, hopefully for most of us, on how to solve ice charts and what they do and why we need to solve for them. Okay? Reaction goes to completion, we use stoichiometry. Reaction goes to equilibrium, we use an ice chart. All right? Don't forget to hit that like button, subscribe. Help me get this channel going so I can retire. See you guys later. Bye.